So for this problem, we have to consider a 300-liter storage tank of a solar water heater system, initially filled with warm water at 45 degrees Celsius. Warm water is withdrawn from the tank through a 2 centimeter diameter hose at an average velocity of 0.5 meters per second, while cold water enters the tank at 20 degrees Celsius at a rate of 5 liters per minute. We have to determine the amount of water in the tank after a 20-minute period and assume the pressure in the tank remains constant at 1 atm. So we have this diagram. We have that the volume of this one is 0.3 cubic meters. So in this hose, it is entering cold water at 20 degrees Celsius, and the volume rate is 5 liters per minute. And warm water is leaving the system in a 2 centimeter diameter and with a velocity of 0.5 meters per second. So for this case, we have to consider the density of water, even though it's cold or warm water, at 1,000 kilograms over cubic meter. And for these systems, first we have to do a mass balance. So the mass that it's going, it's the mass balance. The mass that is going in minus the mass that is going out equals the difference in mass of the control volume, and this is M2 minus M1. So we can calculate the mass, the M1, which is the mass initially in this one. So M1 will equal the density times the volume. So we have these two data. The density is 1,000 and the volume 1 is 0.3 cubic meters. So we have that it's 1,000 kilograms over cubic meter times 0.3 cubic meters. These are going to cancel with this one. So we have this is 3,000 kilograms, and this is this one. We can calculate the mass that it's going in and the mass that it's going out. So the mass that it's going in, we have this data. The mass that is going in equals the density times the volume. But because we have the volume rate, that it's 5 liters per minute, we can obtain this other formula, that is the density times the volume flow rate. And if we multiply this times the difference in time, we could have the volume, and so it's 1,000 kilograms over cubic meter times the volume flow rate, which is liters, 5 liters per minute. And the problem states that the difference in time it's a 20-minute range. So because we have minutes here, we don't have to convert it to seconds. So it's 20 minutes, and minutes are but we have to convert these liters to cubic meters to get only kilograms. So we know that in 1 cubic meter there are 1,000 liters. So we only get 5 times 20 because this 1,000 cancel with this one. So it's a mass of 100 kilograms. And that's for the mass that it's going in. And for the mass that it's going out, we have also the density times the volume, but we have this data, that it's the diameter and the velocity. So we can write it as the density times the velocity times the area times the difference in time. And this is the volume. So we already have this information that it's 1,000 kilograms over cubic meter times the velocity that is 0.5 meters over second times the area, which is P times which is 2 centimeters diameter, so it's 0.02 over 2 squared times the difference in time times 20 minutes. But because we have this in seconds, we have to convert these minutes to seconds. So we know that in 1 minute, there are 60 seconds. So this gives us and this gives us 188.5 kilograms. So we substitute these values in this equation. So we have that it's 300 minus this one, which is 188.5. This equals the mass 2 minus 100. So if we clear this equation, we get that M2 equals 300 minus 188.5. The mass 2 equals 211.5 kilograms. So that's our answer, this one.